Okay, welcome back to session 24, part 2 on beams. We're going to be furthering our discussion about deflection. And in this section, or this part, we're going to be talking about how we go about calculating deflection using the equations that we just derived, okay, to determine deflection across a beam. Now, the big three, all right, there are lots of big threes, I guess, but these are the big three that we'll be using for looking at displacement along a beam are important. And these are what we're going to, be manipulating in our procedure. Okay, and let's start off with multiple steps for being able to use these equations appropriately. Kind of the first thing that may be worthwhile doing is to get a general idea of what the elastic curve should look like. Okay, so if you have loads going downward, right, you get an idea that it's probably going to be a nice smiley face. Okay, if they're going up, it's going to be something different. If you have positive moment, right, that means that you have positive curvature, smile. If you have negative internal moment, that means you're going to have frown, right? So you can get a general idea of what the elastic curve, what the profile of displacement might look like along the curve. Then it's often a good idea to break the beam into regions, okay, between the loads. All right, so like if you have a point load here, boom, that's one region before that, another region before, after it, okay? If you have an overhang and you have some type of roller in the middle or a pin, okay, then yes, that would be another place where you would break it up. Okay, so you can break it into multiple regions. There are some where you don't really think about it because you just have a distributed force across the whole thing. So boom, you just use X across it. But otherwise, we'll talk about this in more depth, right? You think about breaking into different regions. And we should think about boundary conditions a little bit too. Next, we're going to find the necessary expressions for moment, shear, and or distributed loading. And we talked about this a little bit in the last part, that it's not always necessary to do 4 integrals, okay, to get to the displacement. If you can simply get to a bending moment, then you're going to only need to do a couple of integrals. But depending on your boundary conditions, right, you may want to consider using the other forms, okay? But even if we have some boundary conditions for what the big V is, it may make sense to try to figure out what M is first, before we go into this. And we can use, it's kind of the same thing. It's dm dx is equal to v, right? And so that's what this is, but now applied to displacements. Integrate the appropriate number of times, twice for moments, 3 times for shear, or 4 times for distributed loading, okay? And make sure we keep adding constants, so C1, C2, C3, C4, right? And after that, apply boundary and continuity conditions. Okay, we'll talk about continuity conditions in a little bit, but you have a general idea of what boundary conditions are already. We'll talk more about them too. And, how many constants would you be adding? Well, that depends on the number of integrations you're performing. Okay, and so if you're starting from bending moment, then, you only need a couple boundary conditions because you're only going to integrate twice. If you're integrating 4 times, then, yeah, you got to figure out 4 boundary conditions, okay? Boundary conditions or continuity conditions. Okay, and then finally, we can determine the expressions for the slope angle. Okay, and that's this, theta equals dv dx. So dv dx, right, is the first integral off of the moment, okay, times the flexural rigidity, okay, and then vertical displacement, right, is the second integral off of the moment, okay, right there. Okay, so we have all these intermediate steps that we can go from distributed force all the way to displacement. It's kind of neat, and it's kind of beautiful. So this is just a page on how to keep track of the direction of X and using appropriate sign conventions. So, one way to break this beam up is to say, I'm going to define a section x1 and then another one x2, but all with respect to the left wall. Another would be to say, I'm going to come up with an x1 going to the left or going to the right, and then an x2 going to the right, but starting where this other p is. Okay, and still another way to break this up would be to say, oh, I'm going to have going from x1 from the left, and then I'm going to have x2 coming from the right. All right, and depending on how you slice, we know this is a copy of what we discussed previously. When we're looking at the moments on the exposed faces and the shear forces on exposed faces, we want to make sure that we're using the appropriate design convention. Okay, and this may be a more simplified version of what you have here. Okay, so just make sure that if you're slicing and you're exposing the right, V is down, and if you're slicing and exposing the left, then V is up. Now, breaking it into regions also demands that we keep track of slopes, and there's a new convention to introduce here. So if this is actually exposed, so this is a little bit of a shaky thing, a little bit of jagged there, right? So we slice. If we're coming from the left and we're exposing the right, positive theta, positive dv dx, little dv dx, little or d little v dx, okay, can be described as going up to the right. Okay? But if we're coming from the right and exposing the left, it's the mirror image. It's the opposite. Look at this. So coming this way, now we have it coming up to the left. So this is something to keep in mind and to be very careful of. Here are some examples. If we have this beam loaded by P and we say there's a distance D and we're going, okay, to the right, x1, right, is we'll associate v1 with x1 and theta1 with x1. We'll associate v2 with x2 and theta2 with x2. So here we're both starting from the left, okay, and so v1 of d, okay, when we get to this p is equal to v2 of d, no big difference, and theta1 of d is equal to theta2 at d, okay, when we get there, coming from the left. If we come from the left and come from the right, then we need to be a little bit more careful, right? So v1 of d, all right, can be equal to v2 of L minus d, okay? That's fine, right? Because displacement is still vertical. But now we have to flip. We realize that we have a difference in our conventions for the angle. And so this is something that, how do you say it? We'll get you. This is a gotcha here, right? So we want to make sure that we have a theta1 of d is equal to minus theta2 of L minus d, okay? So like at this point or at this, wherever you are along here, right? But if we're talking at the middle, okay, then these have to have opposite slopes, okay, to satisfy this convention. Boundary conditions again, we already talked about them. So we're looking at shear force, moment, vertical displacement v, slope, or dv dx. If we have a roller pin at the end of a beam, then the little v is got to be equal to 0. Okay, that's like over here, or here, here, or here. And the moment, the internal moment, these rollers or pins, they cannot contribute any moment. They can only give like a force, right? That's going to be equal to 0 too. If we have a fixed end, right, and to be clear, these boundary conditions are not describing the jagged slice part. They're describing what's underneath on the opposite side from the jagged region. Okay, so this is fixed and this is fixed. In that case, again, the displacement is equal to 0 at the fixed ends. But now we can go a little bit further and say that theta, the angle, the slope coming out of the wall, is equal to 0 as well. Okay, and for a free end, okay, of a beam, we can say that the shear force, big V, not little v, big V is equal to 0, and M is equal to 0 as well. Okay, and so just to double emphasize, little v is displacement, big V is shear force. Let's do another example. We have the following configuration, and we're going to derive the expressions for displacement across the beam. So what do? First, we write out, okay, what's our general idea for the curve? And we're going to say something like this smiley face. We're going to break the problem into regions. In this case, I defined x1 coming from the left and x2 coming from the right. We're going to take a look at the shear force and bending moment across the beam. So if we can find expressions for these loadings, that's very nice. And you can, go back. If this doesn't come up quickly in your head, it's okay. You'd have more than a minute to figure this out, of course, but go back and look and recall how you go about doing this. Once you've got the shear force, it's not that bad, right? You can say, oh, shear force, right? dV dx is equal to W, and there's no W. I'm going to integrate V, but what am I getting at the boundaries, or at the left and the right side? And I have a jump in the P, which is downward, right? So this should trigger some bells. There's a reaction force P over 2 coming up here, which is opposite of the shear force coming down, right? And if I want to integrate, right, what's the area to get M? What's the area under this curve? Well, it's P over 2 times L over 2. That gives me P L over 4, right? And so that's going to tell us that's what the peak is here. Okay, and we can now write out expressions for M of x1 and M of x2. This is nice. What does this mean? That means that we only have to do 2 integrations, okay? Because we've gotten now to the point where the flexural rigidity times the second derivative of little v with respect to x is equal to m. So for x1 less than L over 2, we start off with that expression I just said verbally, EI, second derivative of v with respect to x1 is equal to m. We plug in our expression for m, and we can integrate and add a constant. And once we've done that, we can integrate a second time and add another constant. And we can do the same thing for x2, okay, on the other side. And we have the first integral giving us a constant C3. Be careful, we don't necessarily want to, how do you say it? We just want to be very careful, okay? And here we have our EIV, all right, here. And we have boundary conditions, okay? So, I guess I got to be careful. I said, if you only need to do 2 integrations, you have 2 boundary conditions, right? But if you have 2 equations, 2 separate regions, right, you're doing 2 integrations, okay? And for this one, and 2 integrations for this one, and these constants aren't necessarily the same, then we need 4 boundary conditions. We still need 2 boundary conditions for each equation, okay? So it is important to look at, how many unknowns you have when you do these integrations. Okay, so interesting stuff here. I think it's interesting, okay? Boundary conditions that we can use, the displacement here and here is equal to 0, right? And that makes sense at these constraints on the right and the left. Continuity, this is interesting, all right? So we can say that the displacement at the middle, coming from the left, and the displacement coming from the right, it's going to be equal, right, at this location. This is a symmetric problem. And now, though, right, same thing we saw just a second ago. If we come from the left and we look at the definition for slope, we come from the right, look at the definition of slope, they are negative of each other. So we write them out like this. Now what do? Well, we can take this expression, okay? Oh, and I guess I should have said, okay, first, knowing that the v1 of 0 is equal to 0 and v2 of 0 is equal to 0, that's nice because it knocks out C2 and C4, okay? Here, using this continuity, what do we get? Oh, this is kind of boring, you say. Well, C1 is equal to C3. That's nice, okay, but I don't know what C1 and C3 are equal to. Now I take this second equation for continuity, looking at the slopes, and I do see that I have a C1 and I have a minus C3 over here, and I have this minus and I have this plus, okay, quantity. So when we solve, we get that 2C1 is equal to minus PL over 2 times quantity L over 2 squared. And C1 is then therefore equal to C1 is therefore equal to minus PL squared over 16, which is also equal to C3, okay, because that's what we got from this condition. So when we do this out, or when we substitute C1, C3, C2, C4 into the equation for displacement with the region having x1, and we solve for displacement with the region for having x2, right? We are able to come up with this expression that we see here. Okay, now, what if we want to use a slightly different approach? Okay, we've done all this is the same, but now we think, oh, maybe there's a different way I can think of the continuity. We can do a little trick. We can say for continuity, instead of having the two expressions where we're saying, okay, displacement is equal to this and it's equal to this, it's equal at that point, and instead of saying the slope is opposite and equal to each other at the middle, we can actually say that the slope, okay, because of symmetry, we can kind of say, hey, look, this has got to bottom out. It bottoms out, and the slope, when it bottoms out, is equal to 0. Does that make the algebra a little bit different or a little bit easier? Yeah, it actually does, okay? So we have this expression, PL over 4 times L over 2 squared plus C1 is equal to 0. And C1 is equal to minus PL cubed over 16. And C3 is equal to minus PL cubed over 16. This is beautiful. This is nice. This is exactly the same expressions. These are exactly the same expressions we got last time, okay, but it's a little bit simpler to do that derivation. And we get this final result, okay? And this is same for x is less than L over 2, right? Really, it's like x1 is on the left side and x2 is on the right side, and you'd write out two expressions. But it's symmetric, so if you're going from the left, you can use this, and if you're going from the right, you can use it as well. And I just wrote it as x. Okay, so the question to solve here now is for a beam that has a moment applied in the middle. Okay, this is an applied moment, m0, and it's actually positive, which means it will have a negative step change. All right, and you can go ahead and start to work on this. And first thinking qualitatively, what's happening? Well, this left side's probably rising up a little bit. The right side's the right side is rising up a little bit. I guess I'm flipped from you, and the left side is going to be going down a little bit. Okay, and the curvature on this side will be positive. Curvature on this side will be negative as it's up. Okay, and so the question is, what is the but the question is, what is the displacement at x equals L over 4? All right, thank you, and see you in a little bit.